Section 8.2 is on constructing, reading, and interpreting graphs of data. So we have several ways of constructing things. One of them is a histogram. So a histogram gives a range of values, gives categories described by ranges of values with rectangles used to indicate how many values are in each category or class. We had used the term class in the previous section. So we notice, for example, if we said something like we can set up a table given class going from 1 to 5, 6 to 10, 11 to 15, 16 to 20, we could have number of values, frequency, of, say, 7, 19, 15, 10, and then the graph, the histogram, would look like, you can put lines at 5, 10, 15, 20, and then we know if you have a box, we'll have the vertical axis go up to, let's make 2, 3, 4, 5, 6, 7, 8, 9, 10 lines. We can make this top line 20. And so we notice that class 1 to 5 has frequency 7. So we count off 2, 4, 6, 7. So we have a box, a rectangle of height 7 from 1 to 5. And then from 6 to 10, where we have a frequency of 19. So we put a rectangle of height 19. Then from 11 to 15, we have that occur 15 times. So 12, 14, 15. We get that rectangle. And then 16 to 20, we've got 10. And so we notice histograms are a quick way of visually summarizing data. We can see that the 6 to 10 range shows up most often. The 1 to 5 range shows up least often. We also notice, something to note is that just by convention, we notice that if we have values, if we have ranges, given as integers, but the values themselves can have decimal values, we notice that we treat values within 0.5 units as being part of the class. So what does that mean? So for the chart we had just done, we had 1 to 5, 6 to 10. If we have the given class again is 1 to 5, 6 to 10, 7 to 11, sorry, 7 to 15. Why did I say that? 11 to 15. (16 to 20), we notice that if we have the potential to have values that aren't integers, our adjusted class will be 0.5 to 5.5, 5.5 to 10.5, 10.5 to 14.5, and 15.5. And 15.5 to 16.5. And so we notice that if we tack on a column for frequency, we notice that if we picked a random selection of values, so if we said 3.7, 9.4, 10.8, 15.3, 17.2, 20.1, 5.7, 10.2, 11.3, 15.2, notice the adjusted class, we want to go 15.5 to 20.5. I don't know what I actually said. There, that's better. Let's just grab one or two more. Let's toss in 5.3 and 10.9. So we notice that we can chart frequencies we notice that the number of values that go from 0.5 to 5.5 are going to be 1, 2, 2 values. Then from 5.5 to 10.5, we're going to get 1, just 1. From 10.5 to 15.5, we're going to get, oh, actually, we have to be careful. 5.5 to 10.5, we actually get 1, 2, 1, 2, 3. That's better. So always make sure you're careful about counting. 10.5 to 15.5, we've got 1, 2, 3, 4, 5. And then 15.5 to 20.5, we're going to get 1, 2, just 2. And we notice we can check. We notice that we count at the frequencies, we've got 12 values. We look at how many values we had. We count off 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And so we notice we haven't missed any. And so if we're going to look at the histogram for those values, we've got 2, 3, 5, 2. And so we notice that our horizontal axis is going to be pretty much the same. We're going to get 5, 10, 15, 15, 20. But now we only have to go as high as 5. So we're going to go 1, 2, 3, 4, 5. So 1 to 5, we've got a frequency of 2. So our rectangle is height 2. Then we've got height 3, height 5. And then back to height 2. So constructing histograms is usually pretty straightforward. We decide on our categories, we decide on the classes, we identify how large each class is, and we've got our histogram. Directly tied to the idea of a histogram is the idea of a frequency polygon. Uses points and lines instead of rectangles. And so we notice that if we had the same batch of data we just used, the idea would be to use the same ranges of values. We still have 5, 10, 15, 20. But now, instead of drawing rectangles, we draw a dot at the midpoint of each spot where the rectangle would have been. So we notice that 1 to 5, we had 2, so we put a dot at the midpoint. 5 to 10, we had 3, so we put a dot at the midpoint at 3. 10 to 15, we had 5, so we put a dot there, midway between 10 and 15, but at height 5. And then 15 to 20, we look at the midpoint, and then we put a dot at a height of 2, and then we connect the dots. So line, 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 and so we get something that looks like a polygon. You notice it's functionally the same thing as a histogram. Mainly it just makes it look a little bit neater. That said, histograms also, the question of which to use is chiefly a question of aesthetic preference. So we notice to construct one of these frequency polygons, we're basically just either drawing or imagining the histogram and then constructing the frequency polygon. So if we had something like 4, 8, 12, 16, 20, that'll do. And then we had a histogram, put that 3, have the frequencies go up to 12, so we could have 0 to 4 goes up to 3, then 4 to 8 we might put at 5, 8 to 12 we'll put at 11, 12 to 16 we'll put at 8, and 16 to 20 we'll put at 4. We notice that we would construct the, we actually want to start at 0 and end at 0. But that's more just a question of aesthetics, giving it a nice starting place and ending place. So we put in all our midpoints. And so we notice that we can go, do you want to draw it that way? There are a couple ways to construct it. Your book usually leaves us some space just to make it look nicer. Oops. So we go up, connect the dots. And that's a pretty straightforward way for getting a frequency polygon. And you'll notice a lot of these methods are all slight variations. Another slight variation is the idea of a cumulative frequency. How are we going to phrase this? So your book calls it a cumulative frequency corresponding with an adjusted class of a grouped frequency distribution, which we noticed rolls off the tongue almost instantly. Pretty much what we notice is that we want to construct. We first look at the frequencies for each class, and then we construct adjusted classes that include all of the data up to the largest value of the current class. So that's a little ambiguous. So what does that mean? The idea is that if we have a frequency table, so if we have class given by, let's stick with 1 to 5, 6 to 10, 7 to 15, 16 to 20, and then frequencies given by 2, 7, 9, 6, we notice that we're looking at the cumulative frequency is the sum of everything up to that category, everything up to that class. And so we notice that the cumulative frequency going from 1 to 5, so we got the class 1 to 5, that just includes 2 values. But now cumulative essentially is thinking of going from 1 to 10, and so you know that's now going to be 9 values. Then for the next category, the next class, we're going to be looking at 1 to 15, and that's going to be 18 values. And then 16 to 20, we're looking at values from 1 to 20, and so we get the cumulative total is 24. And so essentially we notice that now we're thinking of, essentially we could think of how many students scored up to 5 on a quiz. We could say 2. How many students scored up to 10 on a quiz? That'd be 9. How many students scored up to 15? We get 18. And then how many students scored up to 20? We get 24. And so on a graph, we notice that it's clearly going to go up. So if we make a frequency polygon, we notice now we have to go from, we've got 5, 10, 15, 20, as we've been doing so far. And then we need to get up to 24 now. So 2, 4, 6, 8, 10, 12. 14, 16, 18, 20, 22, 24. And so now we know 1 to 5 is going to go up to 2. So we'll get up there to 2. Then 6 to 10, we want to go up to 9. So we'll be there. Then 10 to 15, we notice now we're looking really 1 to 15 bumps up to 18. So you jump up again. And then 15 to 20, we notice is now up to 24. And so this kind of graph lets us see essentially how fast things are increasing. So we notice that we're increasing, the number is increasing faster, 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 and then the rate of increase slows down a little bit. Another variation is the idea of a relative frequency histogram. And so a relative frequency histogram is basically the same thing as a regular histogram, but now instead of using raw values, we use fractions or decimals such that we look at the portion of the data that falls into each class. Oops. So what does that mean? We notice that if we were given, let's stick with same old, we'll stick with 1 to 5. So class 1 to 5, frequency. So we'll have 1 to 5, 6 to 10, 7 to 15, 11 to, 11 to 15, 16 to 20. If we said something like 7, 12, 18, and then let's go with 3, we notice that we can construct relative frequency we notice that the total number of values, if we add up all the frequencies, we're going to get 7 plus 12 is 19, 37, 40. And so we could say the relative frequency is 7/40ths, or that would wind up being 3.5/20ths, which is 0.175. 12/40ths is 6/20ths, which is 0.3. 18/40ths is 9/20ths, which is 0.45. And 3/40ths is going to be 1.5/20ths, which is 0.075. Let's make sure that actually worked out right. Yeah, we notice that those add up to obviously 40/40ths or 1. And if we ran that through our calculator, we would find out 0.3 plus 0.45 gives us 0.75, 0.175 plus 0.075 gives us 0.25, so that we get 0.75 plus 0.25 is 1. And so the advantage of this is it helps when we've got different size groups. So we notice that if we compared that to, so let's just make double bar, we're going to keep the same classes, but now we could have a different group that has the same classes but completely different frequencies. So if we had a frequency of 153, 307, 206, and then we had, let's keep the numbers nice, so that's going to be 500, 600, 666, so we could make that 134. Gives us a total of 800. Double check it, 10, 20, 70, 100, 1, 5, 6, 7, yep, that gives 800. And so we notice that comparing 153 to 7, comparing 307 to 12, it doesn't really, visually, it wouldn't tell us anything. But when we start thinking about relative frequencies, now we can compare a class of 40 to a class of 800. We see that the relative frequency for this much larger group we can say 153 divided by 800. We're going to get 0.19125. 307 divided by 206. Sorry, 307 divided by 800. We get 0.38375. .206 divided by 200, 206 divided by 800, we get 0.2575. And if we take 134 divided by 800, we get 0.1675. And so we notice comparing, we see that the first two classes wind up having similar frequencies, but then the two larger classes, we notice that the largest class shows up with higher relative frequency than that class from 11 to 15. And so if we compare the histograms, we notice that essentially we're just using that same old histogram idea. The only difference is that now every rectangle can be at most 1. So we're essentially looking at so we have the same categories. And so we notice every relative frequency histogram is going to go from 0 to 1. And so we know that first group, we notice that we're going to have 0.75. So it's going to be a little bit short of 0.2. Then we'll have 0.3, 0.45. And 0.075. Oops. Versus the second group, we had 0.19125, so almost 0.2. And then 0.38375, so almost 0.4. And then we had a distinct drop-off for that third category. We had just 0.25. So big drop off. And then we had 0.1675. And so this lets us easily compare the two batches of data with very different group sizes. So that's an advantage of relative frequency.